Picture this. It's August 2023. You've got a massive typhoon spinning out in the Western Pacific, and it is barreling directly toward Taiwan. Millions of people are bracing themselves, and they desperately need to know two things. Where exactly is this thing going? And just how strong is it going to be when it gets here? Well, in this explainer, we're diving into how that exact moment became the ultimate testing ground for a literal technological revolution, pitting 5 different AI models straight up against nature.
I mean, the stakes here really could not have been higher. People needed precise answers to prepare for impact. Now, historically, this kind of heavy lifting was a job exclusively for massive supercomputers. But this time around, 5 brand new AI models stepped into the ring. And what they did completely shocked meteorologists, but at the exact same time, it exposed this one really stubborn, shared flaw that literally none of them could escape.
Okay, to really grasp how wild this leap is, we kind of have to look at how we used to do things. For the last 70 years or so, we've relied on numerical weather prediction, or NWP. And the idea is elegant, but man, it is computationally exhausting. You basically take the laws of physics, turn them into these massive, complex equations, and then run them forward in time. It requires supercomputers the size of actual warehouses, and it takes hours upon hours just to spit out a single 10-day forecast. But then along comes machine learning weather prediction. And the contrast in efficiency here is just staggering. AI labs like Google DeepMind and Huawei basically asked this brilliant question. What if we just stop simulating the physics? Like, what if we just show a neural network 80 years of past weather snapshots and let it figure out the patterns on its own? And just like that, we went from needing hours of compute time on a massive server farm to generating a 10-day global forecast in seconds on a single GPU. The AI is entirely replacing those hard-coded physics rules with pure data pattern recognition. But, here is where the science gets genuinely fascinating. All 5 of these top AI models were trained on the exact same historical data set. It's this set called ERA5. So if they are all reading the exact same data, why do their forecasts end up looking different? Well, think of it like 5 brilliant students sitting in the exact same lecture hall, reading the exact same textbook, but each one takes notes and processes that information in a completely uniquely structured way. Let's actually break down how these models think for a second. First up, you've got FourCastNet v2, which is kind of like the patch cutter. It treats the atmosphere like a giant photograph, slicing it into little visual tiles to see how far apart patches influence each other. Then there's Huawei's Pangu-Weather, the 3D thinker. It acts a lot like an MRI, scanning the height, latitude, and longitude all at once as a single volume. Google DeepMind's GraphCast is the network thinker, mapping the Earth as this huge interconnected mesh of nodes and edges. Then we have FuXi, the relay runner, which splits the 15-day forecast into 3 specialized models that literally hand off to one another to stop errors from piling up. And finally, FengWu, the conversationalist. It treats wind, temperature, and pressure almost as separate senses, like sight, sound, and touch, and learns how they correlate while practicing recovering from its own mistakes. So, with all these distinct styles, how do they actually perform in the real world? Well, Taiwan's Central Weather Administration ran a massive evaluation, a true apples-to-apples comparison to see what happens when they all hit the track at once. And the results? The traditional physics-based supercomputer model, called the IFS, landed directly in the middle of the pack. AI hasn't just caught up here. The top AI architectures are actively pulling ahead. In fact, FengWu achieved an absolutely incredible 10.75 days of skillful forecasting, taking a definitive lead. But hold on, because there is a massive plot twist hiding in the data. When researchers zoomed in specifically on the 2023 typhoon season, they found this glaring paradox. The AI can see the path, but it cannot feel the punch. Yep, the exact same model that flawlessly predicted where the typhoon was going completely and utterly failed to predict how strong the storm would be. It's a crazy paradox when you look at it. For track accuracy, where a lower score means a better prediction, FengWu totally dominates. I mean, it practically locked onto the storm's true path. But then, if you look at intensity error, FengWu actually has the absolute worst intensity error among all the competitors. So the best model for the path is somehow the worst for the punch. How is that even possible? To understand why AI completely whiffs on storm intensity, we kind of have to do a scientific autopsy here. And it starts right at that shared foundation we talked about, ERA5. This is the historical training manual for all 5 models going all the way back to 1940. But here's the catch.
ERA5 operates on a grid resolution of about 28 kilometers per cell, and that fundamentally limits the AI's vision. Think of this first flaw as the resolution wall. If you look at a severe Category 5 typhoon, its intense eye wall, which is where the absolute worst winds and the lowest pressures live, is only about 20 to 50 kilometers wide. But because the AI's training grid is 28 kilometers, it just can't see that tight, fierce core. It only sees a blurred, smeared-out, averaged version of reality across a really coarse grid. Honestly, these AI models have never actually seen a true Category 5 eye wall in their training data. They just see the blur. And it's not just a vision problem, it's literally baked into the math. The models are trained to minimize something called mean squared error. Basically, it's a statistical training penalty, and it practically forbids these neural networks from boldly predicting rare extreme events. Think about it. If a model is unsure about a rapidly changing storm, guessing an extreme Category 5 is going to heavily penalize it if it's wrong. So mathematically, it's just much safer to guess the average. Which leads us right into the regression trap. When faced with a highly uncertain extreme event, like a rapidly intensifying typhoon, the absolute safest mathematical guess for the AI is a conservative average, not an extreme peak. Because of this, every single one of these AI models shares a systematic weak bias. They all systematically underpredict storm intensity simply because the math rewards them for playing it safe. So how do we fix a flaw that every single model shares? Well, researchers found this beautifully simple, elegant workaround. The ensemble. Remember how they all have entirely different architectures? A graph network makes completely different statistical mistakes than a vision transformer. So the researchers just average all 5 wildly different models together. No special weighting, just the mean. And because their unique architectural errors overlap, they just cancel each other out. The ensemble matched the top model's baseline accuracy and completely eliminated any of those catastrophic outlier tracks. And the best part? Because AI inference is so incredibly fast, we don't have to stop at 5. We can do 51. Institutions like Europe's weather agency, ECMWF, have already launched these incredible 51-member neural network ensembles, and they're running them right alongside their traditional models. This completely flips the economics of forecasting on its head. To run 50 physics simulations on a supercomputer, you're talking hours of massive computational cost. To run 51 neural network AI runs on a GPU, it takes about the time it takes you to brew a cup of coffee. It gives forecasters massive safety margins and consensus tracking, all at a total fraction of the traditional cost. But let's bring this back down to reality, right? What does this actually mean for people on the ground in Taiwan? Well, global AI models get the big picture right in seconds. But during Typhoon Haikui, the coarse global AI massively underpredicted the rainfall, guessing somewhere around 130 to 200 millimeters. The reality? Over 700 millimeters of rain cascaded over Taiwan's mountains. To capture those extreme, terrain-driven local events, Taiwan still desperately needs its high-resolution, 15-kilometer local physics models. The AI sets the global boundaries, but the local physics model actually understands the mountains. And that brings us to the very edge of this frontier. Global AI has conquered the massive planetary picture, giving us brilliant, life-saving track predictions in mere seconds. But it still blurs out the most violent, local extremes. So as we push forward into this new era of Earth science, the big question is, how will we successfully merge these lightning-fast machine-learned patterns with the deep, granular truth of high-resolution physics? How do we ensure we don't just see the storm coming, but are fully prepared for the punch? It's a fascinating hybrid future, and honestly, I can't wait to see how we solve it.